Welcome. So today we are going to talk about power series, and power series is a special case where you have something that looks a bit like a polynomial. And so here, in the simplest form, a power series about 0 is going to have a constant plus a constant times x plus a constant times x squared plus a constant times x cubed and so forth. And so you have this form in general for a power series. If you want it even more generalized for a power series about any value a, then essentially all your x's are inside parentheses. The powers are the same, but instead of x minus 0, essentially you have x minus a terms. And that's what we're going to explore in this particular lesson. So let's get to our first example. We want to find what values of x is the power series the sum of n factorial times x to the n power convergent. And typically when you're trying to find an interval or a radius of convergence, you're going to be making use of the ratio test that you saw in the last lecture. And so that's what we're going to do here. And so with the ratio test, and an in this case is n factorial x to the n power. And so for the ratio test, we're looking at the limit as n goes to infinity of an plus 1. So we have n plus 1 factorial x to the n plus 1 power divided by an, which is n factorial x to the n power. And we're looking at the absolute value of this. Trying to manipulate and simplify brings us to the next step, which is n plus 1 factorial, I know is n plus 1 times n factorial, and x to the n plus 1 is x to the n times x. And on the bottom, I'm going to keep it as is. And I could see a few things cancel out. The n factorials cancel out, the x to the n powers cancel out. I know that n is always going to be non-negative, so I could bring that outside of the absolute value. And I know that the limit is with respect to n, not x, so I could bring the absolute value of x outside the limit. And so in my next step, I have this. And this limit is infinity. Which means when we are looking for convergence, remember with the ratio test, it's convergent when this limit is less than 1. And we now see that it's only going to be less than 1 in one very particular case. And that is when x is 0. Otherwise, it is going to be divergent. Because for any other x value, it's multiplied by infinity, so it's definitely going to be larger than 1, which means it diverges. So essentially what the problem is looking for is this piece here. Let's look at another example. And in this case, we want to know when this series converges. And so we go through the same process. We have the limit as n goes to infinity of the absolute value, and on top we have our an plus 1 term, which is negative 3 to the n plus 1 times x to the n plus 1 divided by the square root of n plus 2. And on the bottom, we just have an, which is negative 3 to the n, x to the n over the square root of n plus 1. And so looking to see how we might be able to simplify this, I see that we have negative 3 to the n times negative 3 times x to the n times x over the square root of n plus 2. And multiplying by the reciprocal of the denominator, we just get the square root of n plus 1 over negative 3 to the n, x to the n. And I look to see what cancels out. I see x to the n cancels out, negative 3 to the n disappears. And now I could see that the n terms I could bring, if I want, inside one single square root. And the remaining negative 3 I could pull out as just 3, because when I enact the absolute value sign, the negativity disappears. And we are left with 3 times the limit as n goes to infinity of the square root of n plus 1 over n plus 2. And this, oh, and I lost an x. Let me make some space for that. The x can come outside the limit, still inside the absolute value signs, because we don't know what value of x has. That's part of what we're looking for. And this limit is 1. So that means we want to know, when is this entity going to be less than 1? And that will be when the absolute value of x is less than 1/3, which in interval form corresponds to x between negative 1/3 and positive 1/3. So what we learned from this so far is that the radius of convergence is r equals 1/3. But what we don't know is if negative 1/3 or positive 1/3 should be included inside the interval. At this point, I've started with strict inequalities, x strictly greater than negative 1/3 but less than positive 1/3. And so I need to explore those bounds. So that's what I'm going to do next. So in our first case, when x is negative 1/3, what does that mean? Well, that is going to affect our series where x is negative 1/3. So on top we have negative 3 to the n, and then we have negative 1 over 3 to the n. And that means that the negative 3 to the n's cancel out, and we have an is 1 over the square root of n plus 1. So that's the sequence that we get when x equals negative 1/3. And so I want to investigate whether this converges or diverges, and I might use the integral test here. And so for the integral test, I could see that an is positive, which is one detail. I could also see that an plus 1, which is going to be 1 over the square root of n plus 2, relates to 1 over the square root of n plus 1, which is an, in that it is always going to be less than that, which means that your sequence is decreasing. which is another requirement. So that brings us to actually finding the integral. Remember, it is going to be the integral from 1 to infinity, because your capital N in the integral test at a minimum is 1, even though our counter in this summation starts at 0. And we want to integrate 1 over the square root of x plus 1 dx, which you could rewrite as x plus 1 to the negative 1/2. And if you see the answer to the integral, great. If not, you could always make use of u substitution. But this is going to end up being 2 times the square root of x plus 1. And that is going to be evaluated from 1 to infinity, which at infinity, it is going to explode minus 2 root 2, which just essentially leaves us with infinity, and that means that the series diverges, which in actuality means that we keep the strict inequality because it doesn't converge, at least with respect to negative 1/3. And now we have to look at the next case, which is when x is positive 1/3, and that is going to give us, so when it's positive 1/3, we have a negative 3 to the n power, and we have a 1 over positive 3 to the n power. And so that's going to leave us with a negative 1 to the n over the square root of n plus 1. And so now we need to investigate this. And what you should see in this case is that it's alternating because we have that negative 1 sign there. And so using the alternating series test, we check the requirements. And so we have Bn to be 1 over the square root of n plus 1. And just above, we had demonstrated that not only is Bn positive, but it's decreasing also. And we also need to show that the limit as n goes to infinity of 1 over the square root of n plus 1 is 0. And so since both of these are satisfied, this means that the series converges in this case. And so finally, we have that the series converges for x greater than negative 1/3 and less than or equal to positive 1/3. And so this is our interval of convergence. And so that's just some of what you could do with power series. The hardest part here is remembering to check the boundary values of the interval and to be able to find an appropriate test for convergence that can successfully determine whether it converges or diverges. And so sometimes in the worst case scenario, it's inconclusive, in which case you just need to try something else. All right? Good luck.